So it's a pleasure for me to be here, and the subject is also supernovae, classical physics. I have only one slide with gravitational waves written on it, but didn't bring any signals today. It's an electromagnetic talk about comparisons to observations of supernova remnants. We are now in the phase of 3D supernova modeling, and a very nice conversation over breakfast today. And the first sentence, the person at the table said, "I heard theorists have a problem to explode supernovae." That's not true anymore. It has changed. We have now arrived at the stage of being able to do three-dimensional modeling, and I hope I can convince you that we have made big progress in understanding how supernovae of the ordinary sort, so core collapse supernovae in the 99.9% of all stellar deaths, take place. The project I talk about is mostly financed by this ERC grant, and it's about three-dimensional modeling of the last burning stages of massive stars, which turns out to be very important. Three-dimensional modeling of the explosion mechanism itself in a self-consistent way, so not putting in the energy of the explosion by hand, the symmetry of the explosion by hand in terms of a jet or something, but starting out self-consistently from the progenitor conditions, and finally trying to push forward these simulations as long as possible in 3 dimensions towards possibilities to compare with observations. The main targets of my talk here in this particular lecture are 3 well-studied supernova remnants, GRAB, CAS-A, and supernova 87A. Nearby supernova remnants, well-studied, a lot of information available, so not just a few data points for this event, but a lot of details, and we try to compare with the details in order to connect the models to as many observational aspects as possible. The scenario you should keep in mind is shown here on this slide, my most used one for introductory parts of my talk. So you have this well-known onion shell structure of a progenitor star with the iron core at the center, and then these different shells of ashes of previous burning stages around. And here's a zoom into the iron core. It's like a degenerate white dwarf, size of the moon, but 1.5 solar masses. And that becomes unstable due to microphysical processes mentioned here, photodisintegration of heavy nuclei, but also electron captures on protons mostly bound in heavy nuclei. This makes the core unstable, close to a mass, which is near the Chandrasekhar limit. It's not quite like that because it's a finite temperature object, so not a zero temperature object. And there's a lot of corrections playing a role. And within less than a second, this neutron star is formed from the collapse of the iron core, and then a shock wave is launched by a way I will discuss later. And then this neutron star is left behind and cooling by radiating extremely intense fluxes of neutrinos. This is the introduction I give to the explosion mechanism, actually going back to 50 years of work, starting with Colgate and White with a bright idea that neutrinos could play a role. Then there was a phase of 20 years where people still wanted to believe in the feasibility of prompt explosion mechanism, where just a hydrodynamical mechanism is responsible. A shock wave is namely formed when the neutron star is assembling at the center, and all the infalling outer layers crash onto the surface of the forming neutron star. A shock wave is generated, and this is moving outwards, but with better and better simulations, it turned out that this shock wave is unable to directly disrupt the star. We need the help of something else, and the something else was suggested by Colgate and White in 1966 to be neutrinos. You could believe in magnetic fields, but magnetic fields require amplification. Otherwise, you don't get the strengths where they become dynamically important, and for that you need rapid rotation, and that doesn't seem to be present in the majority of stars collapsing. So these neutrinos generated in the hot, dense neutron star propagate by diffusion to the surface of this neutron star, the so-called neutrinosphere, and then some of these neutrinos, typically of the order of something like 5 to 10% of the electron neutrinos and antineutrinos, 2 of those 6 species of neutrinos produced. These electron neutrinos and antineutrinos at a level of 5 to 10% are absorbed in the material around the neutron star, generating buoyancy. There's also another kind of instability now being termed Zazi. In the very first models, we couldn't distinguish between those instabilities. Now we understand them. So this is a huge sloshing mode and spiraling mode of the shock. I just tried to indicate that by a distortion of this shock wave. It's not spherical, it should be ellipsoidal here. And then this shock wave receives, if it receives enough energy, is pushed outwards and explodes the star. And for that to start and to set in perturbations in the oxygen shell of the progenitor star, still convectively burning oxygen may be important. Stars, which we consider now between some 9 to 10 solar masses on the lower side, or maybe 8 solar masses, 8 at something, up to maybe 100 solar masses, look very different. This is the density profile. When the stars die, when the stars start to collapse, density profile, logarithm of density as a function of logarithm of radius. And you see that there is a big diversity of these stars. Stars with a very steep density profile have a low mass accretion rate onto this shock wave, m dot, while stars with a shallow density profile have a high mass accretion rate. And the problem of this mechanism with neutrinos is that these neutrinos depositing energy have to fight the mass infall rate onto the shock, which creates ram pressure. So it's a competition between effects playing against each other. On the one hand, the energy input by neutrinos, the increasing thermal energy here, but also due to turbulence, turbulent pressure, turbulent energy transport. And on the other hand, the shock expansion damping ram pressure, and both of them are in competition, and what wins will finally decide about an explosion in a supernova or about death in ending up in a black hole. So people in the last 10 years stepwise have understood much better what's going on and how these stellar profiles determine the outcome. And what has been coined is a parameter called the so-called compactness, which measures a mass divided by the radius corresponding to this mass inside of the star. So a high compactness value means that the density profile is shallow, a high mass accretion rate damps the shock expansion, while a low compactness parameter means that the density profile is steep, and therefore you expect easier explosions just because the ram pressure is not that high. So you have here the compactness as a function of the zero H-man sequence mass, and you see from this set of simulations done by Stan Woozy and Alex Heger that there is quite a lot of scatter, and there is a region where you have a high peak in this compactness where you expect that the explosion is very difficult, while there is a region with low compactness values where the explosion is probably easier. So this was one of the outcomes of a study which we did because we understand the neutrino-driven mechanism now much better, also in terms of the physics going on, where we studied a lot of progenitors, actually up to more than 150 solar masses, in steps of 0.1 solar masses, and you see that there is quite a diversity in the compactness value. The progenitor compactness is plotted here, and the red bars indicating successful explosions, while the black bars indicate black hole formation. And then you can see that, well, everything which is here in compactness value above this value of about 0.3 seems to become a black hole, where everything below about 0.15 is going to end up in a neutron star with a supernova explosion. And there is some region in between where both can happen. It seems not to be very well discriminated what's going on by this compactness. So we introduced another criterion based on two parameters measuring the two influences playing a role in the explosion. On the one hand, the mass accretion rate damping the shock expansion measured by this m dot parameter. On the other hand, the neutrino luminosity, which is proportional to the product of these two parameters. So we have two axes measuring the influence of m dot and the neutrino luminosity, and we know already for more than 20 years that there is a critical condition which one has to pass in order to move from no explosion to explosion. This can be mapped in these parameter space of the progenitor structure, so the structure of the star before collapse. And indeed, when we run hundreds of explosion models or core collapse models, we see that we get a nice separation by this critical line in this space of these two progenitor determining parameters, or progenitor determined parameters, where we have black hole formations predominantly up here and neutron star formation down there. So this is what we understand now about the explosion mechanism, and what I want to point out is that there is a non-monotonicity in the parameters, in the explosion properties, like explosion energy. This is the mass of nickel produced in the explosion. This is the remnant mass, neutron star mass. In this case, all these black bars indicate black hole locations. We didn't put the mass of the black holes here on because they are higher than the upper boundary of this plot. And here is the neutrino energy output. And you see that there is some kind of trends, but there is also quite some non-monotonicity. and there is gaps where this compactness is particularly high, where predominantly black holes form, and the other bars are neutron stars. We have plotted in a paper with Stan Boosley and Chuck Zuckbold, we have plotted also distributions of neutron stars and black hole masses. All this, however, in this study published here in these papers for 0H main sequence masses of stars with solar metallicity. When we go to different sets of metallicities, here's a set with the solar metallicity I showed you before. 10 to the minus 4 solar metallicity shows black hole formation cases predominantly, and there's a much wider space of black hole formation, while primordial metallicity can also bring cases with a lot of fallback. These blue cases are supernovae which Ken was referring to, supernovae which make maybe an explosion but at the same time bring birth to a black hole. So these explosion and black hole cases. This can be quite abundant in the zero metallicity universe. So all this is based on simple explosion modeling, either by analytic or semi-analytic arguments, by one-dimensional simulations, or even by some simplified modeling of the explosion based on some understanding how the neutrino energy deposition in competition with the mass infall, the damping effect of the mass infall works. The question is, of course, how do these stars behave when we model the explosion self-consistently, ab initio, as some people want to say, in 3 dimensions? We need to go to 3 dimensions, as I will convince you on the next slide, just because the geometry is much different between 2D and 3D. These simulations are some of the most computer-intense calculations you can do. You have to do nowadays to understand physics problems. Similarly, I would say difficult as climate modeling or maybe cosmological simulations. So we put in a lot of physics, hydrodynamics, magnetohydrodynamics, relativity, nuclear physics, neutrino physics, the progenitor conditions. We have initial value problems, of course. We put in some initial conditions from progenitor modeling. There are the dynamical models, and then we get the outputs which we want to compare to observations. This is what I mentioned, that the 2-dimensional geometry, which was used for 2 decades, which was constrained by the computer power available, is quite artificial compared to 3D. It's not that we didn't want to do 3-dimensional simulations, it was just not possible. A 3-dimensional simulation, because of this 3rd dimension, takes several hundred times more computer time than such a simulation. When we do a 2-dimensional model with decent neutrino physics, we need several hundred cores for the period of months. We need tens of thousands of cores for the period of several months to do 3-dimensional simulations. So we fill half of a supercomputer for a significant period of time in order to study one of these explosion cases. That's also the reason why these many cases I showed you before, exploding them by the neutrino-driven mechanism, at the moment cannot be run in 3 dimensions. We have to do that with some physics understanding and then do the modeling in a simplified way. Now, with the 3-dimensional capability of modeling, the number of successful explosions around the globe is growing at the number of 1 or 2 more models every year for a period of a couple of years already. So this is a list relatively complete of what groups around the globe have produced so far. Oak Ridge is playing a role in the game. Tokyo Fukuoka with Kei Kotake in this group, the Caltech group, and Asin Garching. And well, I will not go through all the details. There is now a growing number of successful 3-dimensional cases. It's difficult to compare these, and I don't want to achieve this in this talk because the neutrino physics and also the hydrodynamics, the grids used for the hydrodynamics are different for the different groups, and there is different approximations in some of these simulations still needed. But at least the growing number of successful cases with different approaches gives hope that we are very close to a solution. I will tell you mostly or exclusively results from Asin Garching because I have all the details, I know what's going on in the simulations, and I can tell you the caveats. This is our first successful 3-dimensional explosion model, which we put out some 2.5 years ago for a low mass star, 9.6 solar mass star in this case, which is not relevant when you talk about the mechanism, a zero metallicity star from Alex Heger. And you see here this familiar mass shell plot, which is just a sphericizing of the 3-dimensional information in terms of positions of mass elements inside of the star, the collapse, the bounce, the shockwave forms, it stagnates for a while, and then neutrino energy deposition, self-consistently computed here in a three-dimensional simulation, achieves to explode the star. Here you have 3 snapshots of this simulation. I don't show a movie, I will show a movie of another case later. And this explosion actually brings an explosion energy of the order of about 10 to the 50 ergs, which is roughly 10% of the canonical explosion energy of a core collapse supernova. Actually, the canonical value is more around 6 times 10 to the 50, so 6 times this value. And you can wonder, is it under-energetic? No, it's probably not under-energetic because it matches pretty well a case which has been studied for decades with respect to its calorimetric behavior. Energy estimates recently published by Chevalier and Young also concluded that the energy of Crab was probably below 10 to the 50 erg. So it seems to match this kind of explosion which we get for low mass stars pretty well. This is another case which we exploded more recently, writing the paper now. It's a 9 solar mass case where the explosion actually is delayed for a bit longer time, 350 milliseconds, and then the shock starts off again, creating a highly asymmetric with a large dipole mode explosion, which will of course also lead to some asymmetric output of nucleosynthesis products. Here's another case for a 20 solar mass star, now a much more massive one, where we had initially on our first set of simulations in 2013, 2014, difficult to get the explosions, so this model failed in 3D while it had succeeded in 2D. And then we started to play a little bit with uncertainties in the neutrino physics sector, which you can easily imagine are plenty. I mean, the neutrino physics in high density neutron star matter is maybe not ultimately understood, and we played with what is called the strangeness correction of the axial vector coupling, which is experimentally constrained. We took a bit on the optimistic side or the extreme side, a large value of the order of leading to a 15% correction of the weak neutral current scattering of neutrinos with neutrons and protons. This is a modest generation, a very small generation change actually, and we still converted the unsuccessful previous three-dimensional run into a successful explosion. And I just show you a movie. What you will see on the movie is just the time-dependent imaging of the explosion in these terms. What you see is an isoentropy surface here. Inside the whitish surface is the protoneutron star. Here is an outer bluish surface, which is the shock, the supernova shock. And first you will see a huge sloshing mode by this standing accretion shock instability. Then there will be strong convective mode. And finally, at about 350, 400 milliseconds after the beginning of the shock formation, the explosion sets in. Let me just give you the chance. Probably it will be the only movie I have time to show. So here you see this isoentropy surface here. Time is proceeding from the moment of core bounce. The outer bluish surface, pretty difficult to see it now, is this shock wave. And here you have seen the sloshing from the standing accretion shock instability, highly deformed at this phase where the instability has actually led to this violent motion of the shock and of the material around the central neutron star. And then at this time, roughly, the expansion sets in. We have to actually go to a larger volume now to show the expansion of the shock wave. So we get this successful onset of a neutrino-driven explosion here. And neutrinos provide the energy input. Hydrodynamical instabilities provide crucial support, on the one hand, by helping material to stay in the neutrino heating layer for a longer time, absorb more energy from the neutrinos. A larger mass of material absorbs energy from neutrinos, not necessarily the individual gram of material. And also turbulent pressure and turbulent energy transport helping bringing the shock energy into the shock wave. There is not all cases which we can in Garching explode by the help of these instabilities, these SASI and convective instabilities, unless we invoke also asymmetries in the progenitor star. Here you see a simulation which Bernhard Müller has done for the last 5 minutes of oxygen shell burning in an 18 solar mass star, creating these asymmetries from a three-dimensional tracking of the shell burning, of the oxygen shell burning. And you see that when the inner silicon core starts to contract, the asymmetry in this convective layer actually grows into a quadrupolar mode. So there is large-scale motions, and the typical speed of the fluid overturn is of the order of 10 to 20% of the speed of sound. And this has a significant influence on the growth of these post-shock instabilities at a later stage. This was demonstrated by us in a simulation which Bernhard continued to run from this progenitor simulation. And once he used the usually applied 1D progenitor conditions, which we then have to perturb artificially on a very small level. And the second time he used the three-dimensional progenitor conditions he had generated himself by running the oxygen burning phase for 5 minutes. And you see that once he does not get an explosion, while with the three-dimensional progenitor conditions, which additionally stir the post-shock medium when these asymmetries fall into the shock wave, with these three-dimensional initial conditions, he can see the launching of the explosion. So this is obviously a non-negligible influence on getting explosions, how the progenitor looks and how asymmetric the oxygen shell burning layer in the progenitor is. Another way to generate explosions or to support explosions is rapid rotation. But in this study, which we did with Alex Summer's work in Garching, published in APJ now, we needed quite a lot of rotation in order to support the onset of the explosion, actually too much in order to be compatible with predictions from the stellar evolution side or also from astroseismological constraints. Summary at this stage. Two-dimensional models with relativistic effects have begun to yield explosions for quite a while already. Now three-dimensional modeling has begun and confirms some of these successful cases, but in 3D the explosion is more difficult to get. The explosion energy is not determined after a few hundred milliseconds, but some of these simulations have to be run out to many seconds in order to be able to name the value of an explosion energy, and that of course makes it very difficult in 3D still to determine the explosion energy in self-consistent models. Several seconds of three-dimensional simulations with this complicated microphysics is by no means easy to achieve, not even on nowadays computers. The stars below about 10 solar masses explode relatively easily. We don't know whether all of them, the models differ, whether all of them explode, but we get explosions successfully for quite a subset of them. First three-dimensional simulations of 15 to 27 solar mass stars have also been put out in the literature, but in Garching we noticed that it's not so easy. We think we have the best microphysics. We have also a very decent treatment of the neutrino transport. The simulations, however, still need higher resolution for convergence. We tested this recently, and we also have tested the influence of some approximations in the neutrino transport sector, which this is not bothersome. The resolution may be needed to be a factor of 2 higher to get convergence, maybe even a factor of 4, but that is absolutely unfeasible at the moment with these self-consistent simulations, including all the neutrino physics. The progenitors provided by the stellar evolution modelers in 1D spherical symmetry are really bothersome. I showed you a case where we had only obtained explosion when we used the asymmetries we generated ourselves by creating following oxygen burning for 5 minutes. We are now running a 19 solar mass star to do a similar thing. And then we are always bothered about potentially missing physics, neutrino flavor oscillations. Here's a slide which I just flashed very briefly because probably I don't speak to an expert audience here. What we recently, for the first time in supernova modeling, included is the presence of muons. This is another heavy lepton species with a rest mass energy of about 105 mega electron volts. There was a canonical thinking in supernova physics that this can be neglected during the supernova phase, maybe not in the neutron star formation period following later. But it turned out that this inclusion of the muons actually also helps the explosion. Here is a case without muons, in 2 dimensions, however, not 3D yet. The 3D model is still running. No successful explosion, while with the muons included, it also yields an explosion. So including muons is another aspect of microphysics going into a favorable direction for getting explosions. So this is now the end of this. I skipped this. Question now is all this what we are doing compatible with what we see in nature? Or how can we test the simulations we do in 3D? How much time do I have? I didn't follow. When did I start and how much time is left? Just want to know. Okay, I have 15 more minutes to give you a brief impression of what we have done over the past couple of years to actually connect the three-dimensional explosion modeling to observations. Here is a long list. I don't talk about all of these things. We have, of course, predicted neutrino signals, and we have predicted gravitational wave signals. In both cases, for measuring them, we have to hope for a galactic supernova. When this happens, nobody knows. I tell you, I announce here publicly, I have a bet that it happens until my retirement in 10 years. I hope it will succeed. The gravitational wave community was so lucky. I hope that the neutrino people, the neutrino detector people who have also worked on their detectors for a long period of time, building up facilities like IceCube, building up facilities like Super Kamiokande, now working on Dune and Juno, that these big facilities will, within the next 10 years, capture a galactic supernova neutrino signal. Gravitational waves, similarly, we will see gravitational waves from such a core collapse event only if the event is in the galaxy. Outside of the galaxy, I have no hope that we will, in the very near future, detect those gravitational waves. So, neutron star kicks, asymmetric mass ejection, and large-scale mixing asymmetries, light curve, and in particular, supernova remnant morphology is the subject of what I will present in the following slides. When we talk about now connecting the explosion modeling in the inner core on a scale of about maybe 1,000 kilometers or so to the explosion modeling, we have to actually bridge a huge scale, a space span of scales, actually factors of tens of thousands. And you can imagine that these simulations are not easy to be done. So we start with the interior physics, creating the asymmetries, beginning with which the explosion begins, and then follow the secondary asymmetries growing by Rayleigh-Taylor instability, in particular at the carbon-oxygen-helium interface and at the helium-hydrogen interface. There is secondary multidimensional asymmetries growing from the fact that the shock wave moving through the star over a timescale of hours to days is decelerating and accelerating, and this creates in this acceleration-deceleration phase unstable density pressure gradients which break up and start to make Rayleigh-Taylor instabilities, and that actually is then finally superimposed on the existing on the instabilities existing at the time when the explosion begins. And we have to simulate all of that self-consistently, so we have to start with a neutrino-driven explosion in 3D and have to continue until the shock expands into the circumstellar medium in order to see the morphology of the remnants developing. This is again zooming back into the first seconds of the explosion where you had seen these asymmetries connected to the beginning of the explosion by the neutrino-driven mechanism. And you see also a large asymmetry, large-scale asymmetry in many of the simulations of the ejector. So on one side, the explosion is stronger, while on the opposite side, the expansion of the ejector is more slow because the shock wave didn't receive that much energy by neutrino energy input. And you can easily imagine that an asymmetry of the explosion leads to a kick of the neutron star, and that is exactly what we see. We see the neutron star actually being kicked in the direction opposite to the stronger explosion. So here's a strong explosion. The neutron star receives momentum in the opposite direction. And we calculated a set by triggering the neutrino explosion mechanism in a bit simplified way, not all the neutrino physics in high sophistication. We triggered 20 explosions of three-dimensional simulations. And then we got a large spread in the explosion, in the kick velocities here. In this record holder case, we have, at that time, we had 700 kilometers per second for the neutron star. Now, Arnob Wongwatarat, doing these studies in my group, has one case with more than 1,000 kilometers per second. So we can actually get very high kick velocities by these hydrodynamic instabilities taking place during the first second of the explosion. What is interesting for comparison to observations is asymmetries in the explosive nucleosynthesis. And here you see, this is the neutron star kick direction. This is the direction where the explosion is stronger. You see much more nickel being produced in the hemisphere where the explosion is stronger. Here is the nickel clumps produced behind the outgoing shock wave. These pockets here contain nickel. Nickel is not distributed in a shell. It's in pockets, in knots, in clumps when the explosion sets in. Here you see it visualized in a different way. Large neutron star kick cases, 550 kilometers per second, 600 kilometers per second for 2 runs. The asymmetry is extreme. We have most of the nickel being produced in the opposite hemisphere in both cases. small neutron star kicks, the distribution, here's the arrow for the kick direction, the distribution of these innermost nucleosynthesized material is much more symmetric. This has been used as a motivation to look at supernova remnants. A collaboration here done with some group in Japan, where data were available of X-ray observations of these supernova remnants, and in particular, they could identify the location of intermediate mass elements between about neon and the iron group, for which we have predicted these large asymmetries, and for these supernova remnants, of which I show you the set of, also the neutron star kick was known, or is known. And actually a very careful analysis of the remnant, where is the center of the explosion, where is the center of the X-ray emission, what is the direction of the neutron star. I don't go into all these details, it's just a summary slide here. But in all of those cases, you can see that the neutron star is moving opposite to the center of the intermediate mass elements seen in those remnants, seen to be radiating and to be ejected with high velocity in the opposite direction. So that seems to confirm our hydrodynamical kick mechanism, in contrast to what has been put out as a neutrino kick mechanism by other particle physics connected groups. We have also even a comparison of the asymmetry of this distribution and the neutron star speed. So there's a correlation which we predicted from the theoretical side, and the model, the data from the observational from the remnant observations seem to be compatible with this prediction of a correlation of the asymmetry of the intermediate mass element distribution and the neutron star kick. Cassiopeia A is a very interesting case because it's studied in almost overwhelming details, also with respect to the symmetry and distribution of elements. And what's particularly interesting was here published in a paper in 2014 in Nature by Gravenstetter. Namely, they had a space determination of the distribution, spatial determination of the distribution of titanium being co-produced with iron during the early phase of the explosion. And what turned out is that from the observational side, the titanium is mostly located in the opposite hemisphere to the neutron star kick, which is also known in the Cassiopeia A remnant. Again, compatible with what we predicted. In the previous analysis of the 6 remnants, there was also Cassiopeia A. Here we have a direct determination of titanium-44 by its radioactivity and the X-ray lines created by radioactive decay of titanium-44, and you see it's confirmed. Titanium-44 is produced. So how does it compare to one of our model simulations? Here you have the observations again, and here you have our model, which we think is most close to the morphology of Cassiopeia A. I put the neutron star kick direction in the same direction as on this observational plot, and you see most of the iron and titanium are ejected in the opposite hemisphere. When you wonder where do you see iron, you have to take into account that iron is heated by the reverse shock moving inward only in its outer parts. So you would see from the iron these parts, while titanium is shining in the whole region. Titanium is still radioactive, while iron is a decay product of radioactive nickel, which has already decayed hundreds of years ago. Yeah, the total production of titanium-44 is also compatible with what has been diagnosed for Cassiopeia A. Here's our theoretical result, 2 cases with an uncertain reaction of 44 titanium, alpha proton reaction to 47 vanadium taken into account. So with a recent rate determination for this reaction, we actually produce even a bit more. So this is a theoretical range where we are, and this is the observational regime. Cassiopeia A and 87A have an astonishingly similar output in 44 titanium. These are the only 2 supernova remnants in our galaxy where we have a clear determination of titanium-44, and they seem to be an outlying, they seem to be outliers with respect to their amount of production of 44 titanium. Other morphology aspects. This is a distribution of elements from argon, neon, oxygen through iron from an analysis done with a lot of observational data. And here you see these purple iron clumps. I show you the plot again here, where the reverse shock position is indicated on the plot. So this is the observational distribution, and this is the model I just showed you. So this is, I roughly indicate the reverse shock location here on this theoretical result. We would see at the moment clumps of 3 big regions where iron is located, exactly compatible with what the remnant at the moment shows. This is an observational visualization of observational data from this three-dimensional morphology, which one knows for Cassiopeia A. So the line of sight is here to the observer. It looks like a thick shell. You can wonder, is the remnant I showed you from the three-dimensional modeling also shell-like? Yes, here's the front view, here's the top view, here's the side view, and you see that we also can reproduce this kind of sheet-like, shell-like structure here in our three-dimensional simulations. Developing naturally from instability starting at the onset of the explosion by neutrino heating. Summary of Cas A. So we can explain the high titanium mass by multidimensional modeling. We observe the observed titanium velocities, the morphology, and the titanium distribution, the neutron star kick velocity, and ejector distribution. We also understand why titanium-44 is absent in some regions where you see high concentrations of iron. There is open questions concerning Cassiopeia A. Why did Cassiopeia A and supernova 87A produce significantly more titanium-44 than other supernovae? And what causes these strange jet, anti-jet features which people have claimed to be visible in the Cassiopeia A remnant? We work on that. It may be connected. Here is the jet, and the anti-jet is hardly visible down there. Not in this image. There's better images. We think this may be connected to pre-existing, pre-collapse oxygen shell asymmetries. Supernova 87A. You didn't give me a sign yet. Supernova 87A is a problem with respect to the determination of the progenitor. We don't know exactly how the progenitor looked, so we explore different suggestions, published in the literature. First model by Stan Woosley some 30 years ago, Ken Omoto's model of the late 1980s, right after supernova 1987A had exploded. This is the 10-year anniversary model produced by Stan Woosley. This is a 20-year anniversary model. So Stan produced in a sequence of gaps of steps of 10 years, he produced different models for 87A. So this is the onset of the explosion, about 3 to 5 seconds here after the beginning of the explosion. And this is the later asymmetry when the shock breaks out from the stellar surface. Actually, it has broken out. It's nearly a day now. The stellar surface is reached within a couple of hours for these blue supergiants. And this is well after the shock breakout from the stellar surface. And all of these instabilities at the different composition layers have interacted and have created some asymmetries. And we wondered, how does that compare then? How does this mixing achieve? This is nickel, actually. Highest nickel velocities here, more than 3,000 kilometers per second. How does the nickel mixing help to shape the light curve? Do we reproduce the light curve with these models? And here's the set of simulations I just showed you, and here's the data of the light curve observations of 87A, and you see that, well, the agreement is moderate. We have a problem here. We have a problem that the peak is too short. The best case still is the B15 case from Stan Woosley, but it's also too short here. So what's the problem? The stars are too extended, and there is too little mass in the helium core at high densities. We have a new model from Stan now where he tried to reproduce this progenitor location in the temperature luminosity diagram better by this model W18X. And you can see that also this new model here is not better fitting the light curve. So what's the problem with 87A? Well, there was a recent suggestion by Heger and Monon, going back to original ideas by Phil Podsiadlowski, that supernova 87A has undergone a binary evolution. That's also the reason why there is the ring structure, probably. And Heger and Menon had produced a couple of progenitor models evolving in a binary and then actually in the end matching this temperature luminosity location of the progenitor of supernova 87A in a Hertzsprung-Russell diagram. And using these more recent models, we get pretty interesting improvements of the light curve fitting. Maybe not perfect, but the stars are smaller because of this binary interaction, so we can better reproduce this dip in the light curve, and also the densities in the inner parts of the helium core are higher, and for that reason we have more luminosity at later stages before we end up in this radioactive decay tail. So that's promising. These results are still preliminary. Alex has given us an improved set of models because in the original set there was a small problem still, so we are running the models now. Morphology of 87A asymmetries, yeah. Here is the iron and silicon distribution from observations, VLT and HSD observations by Larsen et al. And we plot in the same velocity space, we plot the ejecta from one of our explosion models. Actually, this inner sheet is not visible because there is light reflection from the ring, from the 87A ring, and they cannot, this is low velocity contribution, and they have to exclude the inner parts. We did the same here. You see the morphology fits pretty well. We do also some comparisons to carbon oxide and silicon oxide molecular emission observed in supernova 87A. Here's the ring actually, and this is a ring-like inner structure formed from carbon, oxygen, and silicon molecules. And here you see the same orientation as before. Detailed analysis of observations compared to our explosion models reproduces this inner hole and also the clump size. So there is no large-scale asymmetry which points to rapid rotation, jets or anything. It's clumpy. Yeah, I stop here. Don't show this summary slide. It's on this. Thank you very much.
Thank you very much. This is really
Thanks. Can you talk a bit more about the impact of progenitor rotation on your explosion models? Those of us who think about GRBs, right, we think about stars that are rotating very rapidly.
That's not what I talked about. Ken Nomoto has talked about GRBs. Paolo Mazzali will talk about GRBs. I don't want to take the story from them. GRBs are a very small subset. We think less than 1%, maybe less than 0.1%, around 0.1%. This is a very small subset of supernovae, which is not the topic of my talk. In those cases, unquestionably, rotation plays a role. For the ordinary core collapse supernovae, in 99.9%, stellar evolution modelers tell us that magnetic fields in combination with rotation lead to a lot of angular momentum loss from the stellar core. The stellar cores during the late stage of stellar evolution, going through a red giant phase, spin down, and at the onset of collapse, the stellar core rotates very slowly. If you want to have rapidly rotating stars, you have to either invoke binary scenarios or you have to avoid the red supergiant phase where this angular momentum and mass loss takes place. This seems to be compatible only with the evolution tracks of a very small fraction of stars going to supernova core collapse.
Thank you.
Thomas, very nice combination of early and late stuff. You showed your first model had too little energy, then you did something to another mass model, you got the explosion. Can you just recap the energies you get? And if you apply the same corrections to all models, say to the neutrino coupling, how would those energies change?
Well, as I told you, one of these simulation runs is half an hour on 16,000 cores of a supercomputer. So we can get 2 models done in a year. And the result we produced is about 2 years ago. We meanwhile studied some black hole formation cases because some referees of our computer time proposals actually said we would better look at black hole formations, more interesting than supernova explosions. So we did that. We have no other model where we use these corrections. We have some runs in 2D. The explosion energies, if the explosion is successful, which in 2D is actually pretty regularly happening, 2D is favorable for explosions, the explosion energy is not so much changed by these modifications. The point is that these modifications in the microphysics matter most when the models are marginal and you don't get them lifted beyond the threshold of an explosion. So that's are the most interesting cases, and we have not been able to study more than this one explorative case so far because of computer time constraints.
Thank you very much. We have a very last question.
In SN 1987 case that 20 or so neutrinos were detected, and from them that the total energy of the emitted neutrons are estimated, and this just agree with the binding energy of neutron star. However, in the next time, super Kamiokande will detect 5,000 or 10,000 of neutrinos. From them, what do you expect to get a very confirmed evidence?
So we will get a lot of information, not only because we have super Kamiokande, but because we have Ice Cube. We will have hopefully Juno. We will hopefully have June in the United States. June will be able to measure a similarly good signal in electron neutrinos, not electron antineutrinos, which all other detectors measure in precision. Combining all the information, we will get information how the nucleosynthesis proceeds, what the YE in the star is. We will get time-dependent information of the neutrino luminosity, which informs us about the dynamics of these hydrodynamic instabilities, because what I showed you as sloshing mode of the shock, as spiral mode, modifies the neutrino emission in a time space. So we get quasi-periodic neutrino emission modulations. We will get spectral information of the neutrinos evolving with time. With all that, I think we will have the best so far existing access to the microphysics, or to the dynamics and to the physics going on in this kind of extremely exotic scenario in the universe.
Thank you very much. That's the last one, but I'd really make the last one. I think there's a question for me.
Well, actually, I have two questions. One is, you mentioned the importance of this deformation of the oxygen burning shell. Do you get a significant contribution also for the energy of the oxygen burning shell, or it is just the shape that it matters?
What matters is actually the perturbations which are created in the infalling flow, in particular with respect to the velocity fluctuations, which then feed back into density fluctuations once the matter reach the shock wave. And this leads to shock deformation, stirring the instabilities behind the shock and leading to a faster growth of these instabilities. Energy-wise, there is no significant difference. We are talking about energy differences on the level of a few percent by oxygen.
Well, the supernova is few percent of the total binding energy. So, but it's few percent of the few percent.
Of the few percent of the few percent.
Okay, and the other question is, does all this convective motion and all this turbulent motion, does it lead to any gravitational wave which can be?
Yeah, sure. I don't have time to show all that. Yeah, of course, we have a paper out where we analyze the 3D simulations with respect to the gravitational wave signal. There's two interesting contributions to the signal. One comes from the Sarsi sloshing, which creates a quasi a low frequency 100 to 200 hertz signature. And then there is another signal contribution, pretty robust in all simulations, coming from the neutron star. But this signal has a high frequency, is a high frequency component beyond 1000 hertz, so a bit harder to measure.
And this will be detectable to which distance?
About 5 kiloparsecs distance. Yeah.
So it has to be next door.
It has to be next door in our galaxy, yeah.